Okay. What this means is that now I'm at 6.149, right? So all the way over to about 6, here I am. My bug has moved to the right. I'm at 6.149. But again, I'm not, that. What is that Y value consistently? 2. Right? Does this follow my little sign chart? Did I move to the right until I hit 1.153 seconds? Yes, I'm not graphing. Because initially in the problem, it said the position of a particle moving along the line y equals 2. Okay? So you have to remember that S of t is just my position. It doesn't have anything to do with the y coordinate. I'm not graphing against time right now. Right now, all I'm graphing is my bug moving along this line. So here's my bug now. Okay, it's a spider. Thank you. Okay, then I get to 1.53 seconds and my bug stops and goes, ah, I need to go the other way, right? And he moves the other way for until I hit not for 3.18 seconds, but until I get to the total time, 3.18. So where is he at 3.18 seconds? So use your stow again. This time stow x is 3.18, second enter, negative 2.186. Does that make sense that that's where he is? Yes, because he started tracking back the other way. He said, wait, I gotta go back. Negative 2 point, what did we say? All right, so here's my little bug. He turned green, he moved left, okay? The other value, right. Now, do I know where he stopped? I don't know where he stops because it doesn't say he stopped after 8 seconds or he stopped after, but all I know is once he got to this point, okay, so he started going, he turned around to go back home because he forgot something. He stopped there and said, I'm not going all the way back home. And he turned back around and said, I'm going originally the way out. And he keeps going that way forever or until time stops. Does that make sense? So now could you describe that in words? So I start at the point negative 5, 2 and move right for how many seconds? Notice the difference in this and the difference in this. Okay, so I move right 1.153 seconds and stop at the point. What's my point? 6.149, comma 2. My bug changes direction. And then he moves left. They'll probably define something. It'll probably be like a car moves at a constant or something like that. It's very rarely just a particle. It's usually they try to make it applicable as something. All right. My bug changes direction and moves left until. Whoa, Nelly. No, I just messed up my thing. And moves left until time 3.18 seconds. At the point, where am I then? Negative 2 point, stop. 2.1862. Then it changes direction one final time. I love this problem though. And moves right forever. Thank you, Van. That's on my recording. I'm sorry. Now I can answer the rest of the questions. Part B says, when does the... Oh. Let's finish this one problem, and then we'll take a little break. How do you know when it speeds up? Look at your sheet that I gave you on...
What about the acceleration, though?
What about acceleration? Yeah.
What's the difference between velocity and acceleration?
No, we're looking for speeding up and slowing down. What's it say on the sheet? Did I not put this on there?
Positive acceleration means velocity is increasing. Yes, I know this. So,
all right, so speeding up.
Acceleration makes the velocity. Oh, so whichever one is follows. So at 1.5, 1.1. Yeah, your velocity is increasing. But what about your acceleration? You gotta include that too, though.
So it's actually, let's look at our velocity graph. Negative, what's it, look at this graph. And let's talk about acceleration for just a second. For this first piece right here, when it's moving to the right, we know that velocity is positive. What is acceleration there? Positive or negative? Positive, why?
I just want to say that because
the acceleration is actually negative there. Slope. Acceleration would be the slope of the velocity. Okay. If you look on my desk, there's a wireless charger, but you have to plug it into like a computer and then put your phone on it. All right, look at the bottom piece.
At least I don't look like so.
This is where I'm changing, right? All right. Here. From here to here, what is happening? Velocity is what? Velocity is negative. What is acceleration?
Velocity is negative. And your acceleration?
Is also negative. Because it's the slope and it's decreasing. How about this next piece? This piece right here. Velocity is still negative, but acceleration is positive because it's moving up.
Wait, which line am I looking at? Which of these lines are you talking about? Wait, no, this is so confusing. You're talking about this? Come on, this right here?
Yes. And then this piece, I'm getting to a point here. We've done more notes in this one problem. This is really what I wanted to get to today anyway. All right, so this piece right here, velocity is what? No, is it positive or negative? Positive. Here's the key part, when acceleration and velocity have the same sign. Okay, when velocity and acceleration have the same sign.
Velocity and speed.
Then your particle is speeding up. Does it make sense?
I missed that.
The bug is going faster. Okay.
What is velocity? I feel like there should be some sheet where we can define velocity and acceleration.
It's speed.
No, because
All right.
What is the sign?
Let me answer the rest of the questions. I've lost about half of
I'm
this
trying
point.
to.
I know. But okay, so slowing down happens when the signs are opposite. Speeding up, that's a key point. Write it down somewhere. It's important.
I wrote down when velocity and acceleration are opposite. No, we're not saying it.
Same sign, speeding up. You might want to write that on that reference sheet or your notes. They can both be negative, and it's still speeding up. It just means it's going backwards. All right, same sign speeding up, opposite sign slowing down. All right, part C, when does the particle change direction? We've already found this. The particle changes direction at 1.153 seconds and 3.18 seconds. The zeros of velocity. This bottom is velocity, this top is the position. Right. I did. I graphed it and found the zeros. Yep. When is the particle at rest?
Well, it would be there at that zero.
It would be at those same points, those same zeros. Where it's changing directions is it's also at rest. Could it ever be at rest but not change direction? When?
When it just stops and then keeps going. Yeah, maybe like that.
Okay, but what does the velocity graph look like at that point?
Yeah.
It can be. Wait. So
When would so? What am I asking?
What are you asking? It can be at rest.
When can I have a zero but not go from positive to negative or negative to positive?
It would just be like.
What would that look like though on a graph?
If it never crosses a tangent.
If the vertex is sitting there at the zero, it rests right there, but then it picks right back up. Velocity, if this is velocity, then that means the velocity is always positive, which means it's always moving to the right, but it does stop. It does stop to rest. It does stop to rest. All right. Describe the velocity and the speed of the particle. We have already done that. When is the particle at the point 5,2? Well, or negative 5,2? At the beginning, that's its starting point. Dan, when is the particle at the point 5,2? 2 is my constant. It's always at 2. So the real question is, when is the position, which we said was x of t, when is it at 5? And so this is a calculator problem, so I would most definitely say 5 equals 2t cubed minus 13t squared plus 22t minus 5. And I would, oh, that's, yep. I was about to do the same thing, Lizzie. Yeah. I would do this on my calculator. Set it equal to 0 so I can find where it crosses. Absolutely. But, well, it's going to be 2t cubed.
You put down 2 there.
That's fine.
That's not.
Minus 13t squared plus 22t minus 10. And it asked me when is it, and when it, so it's at, it hits that, it makes sense that it hits that more than once. Do you understand why it hits it more than once? Because look, it's past 5.2 here. So it went, shoop, it passed it. It went back, it passed it again, and then it went back one more time forever. So it passed it 1, 2, 3 times. I should have 3 zeros on here, and I do have 3 zeros on here. So it passed the point, so it was at the 0.52 at 0.745 seconds, at 1.626 seconds, and at 4.129 seconds at all of those positions. So 5 and 6, we'll just start with 6, that's fine. We'll start 6 through 8 instead of 5 through 8. 7 and 8. Just start with 6, don't do 5. Start with 6. That way you don't have quite as much, because we were gonna do 6 together in class. I had that written down as one to do together in class. But for number 7, you're going to trace the function. Think about tracing the function here. Look at things like which part has the steepest slope. Okay, where are the peaks and the weakest points, things like that. And then we're going to try to sketch a graph of the derivative. Okay, remember how you did on your test where you sketch the derivative. The other one I want to talk about. Yeah, there's the directions below it. Number 8 is good. That's a draining a tank type problem that shows up more often than not, mostly as, I don't know, we had one a couple years ago that was an FRQ. Draining a cylinder tank or something like that, or a conical. Okay, thank you, Van. 28. All right, suppose the weekly revenue in dollars, guys. Let me write this. I'm telling you, nobody's even paying attention.
Would that be drainage? What's that code?
This is to help you with number 28, guys. This means selling or producing one more. Okay. The derivative is giving you the cost of producing just one more. And for number 28, change in revenue of selling 6. It says 5, but make it 6. So use R prime of 5, not, why did I write that? Oh, where it says 6, it should say 5. Because it says, use the function R prime to estimate the increase in revenue that will result increasing sales from 5 desks to 6 desks. I'm going to use R prime of 5 there, not R prime of 6. Well, because if I want to know the rate to get to the next one, I use the one prior to it. So if I want to know the increase in revenue from 5 to 6, then I would take the derivative at 5 and not at 6. At 6, that would give me the revenue at 7.
Okay.
All right, that's all I got. I'm done.